In this video, we're going to talk about the dot product of vectors in Rn. Let V be the vector with entries v1 through vn, and W be the vector with entries w1 through wn. These are two vectors in Rn. The dot product of V and W is a scalar given by V dot W equals v1 times w1 plus v2 times w2 summed up through vn times wn. Essentially, what we're doing is we're multiplying the corresponding entries of the vectors, then we sum up those products. Let's do a few examples. So here we want to calculate the dot product of V and W. In our first example, V is the vector 2, negative 5, and W is the vector 3, 6. So the dot product V dot W is the product of their first entries, so that's 2 times 3, plus the product of their second entries. That's negative 5 times 6. So we get 6 and then minus 30, or negative 24. In our next example here, we have that V is the vector 1, 2, 3, and W is the vector 5, negative 3, 4. Their dot product, V dot W, is the product of their first entries, so that's 1 times 5, plus the product of their second entries, so that's 2 times negative 3, plus the product of their third entries, 3 times 4. So that's 5 minus 6 plus 12, or 11. In our last example here, we have the vector V with entries 2, negative 1, 1, and W with entries 1, negative 3, negative 5. This time V dot W is going to be the product of their first entries, so that's 2 times 1, plus the product of their second entries, that's negative 1 times negative 3, plus the product of their last entries, so that's 1 times negative 5. So this gives me 2 plus 3 and then minus 5, which is 0. So next I want to talk about the length of a vector, and it turns out we can calculate that using the dot product. Suppose that I have a vector v on the xy plane with components a and b. If I want to find the length of this vector, I can draw a triangle with base a and height b, and the length of this vector will be the hypotenuse of that right triangle. So using the Pythagorean theorem, I know that the length of v is the square root of a squared plus b squared. Now this idea can be generalized to vectors of any dimension. We say that the length or magnitude of a vector v with entries v1 through vn is the length of the arrow when we draw it in Rn. We denote the length of v by writing v with bars around it. Now we calculate it by doing the square root of v1 squared summed up through vn squared. Now notice if I take the vector v and take the dot product with itself, well, this would be the product of their first entries, so that's v1 times v1 plus the product of their second entries, v2 times v2, summed up through the product of the last entries, vn times vn, which is v1 squared plus v2 squared summed up through vn squared. So notice that this expression is what's under the square root in the length of v. So we can say that v dot v is the square of the length of v. Or we can also say that the length of v is the square root of v dot v. So let's look at a few examples. So here we want to find the length of the following vectors. In our first example, we have the vector u with entries 3, negative 4. So first we can calculate u dot u. That's the vector 3, negative 4 dot 3, negative 4, which is 3 times 3 plus negative 4 times negative 4, which is 9 plus 16, or 25. Now the length of u is the square root of u dot u, so that's the square root of 25, or 5. In our next example, we have the vector v with entries 2, negative 1, 2. The dot product v dot v is 2, negative 1, 2 dot 2, negative 1, 2. So that's the product of their first entries, that's 2 times 2, plus product of the second entries, that's negative 1 times negative 1, plus the product of the last entries, which is again 2 times 2. So that's 4 plus 1 plus 4, or 9. So the length of v is square root of v dot v, which is the square root of 9, which is 3. Let's look at one last example. Let w be the vector negative 4, 2, 3. So here w dot w is negative 4, 2, 3 dot negative 4, 2, 3. So that's negative 4 times negative 4 plus 2 times 2 plus 3 times 3, or 16 plus 4 plus 9, which is 29. The length of w is the square root of w dot w, and that's the square root of 29. Next, we'll talk about how the dot product can be used to find the angle between two vectors. Suppose that I have two vectors, a vector v and a vector w. Let's call the angle between v and w theta. It turns out that if v and w are two vectors in Rn, and theta is the angle between v and w, then v dot w is equal to the length of v times the length of w times the cosine of theta. Now, we won't go through a proof of this theorem, but essentially what we want to do is make a triangle in this picture, draw a vector here, which is w minus v, and use the law of cosines on this triangle. So let's now use this theorem to help us find the angle between vectors. In our first example here, let v be the vector 2, negative 5, and w be the vector 3, 6. Now, to find the angle between v and w, we need to know what v dot w is, and we need to know the length of v and the length of w. These two vectors were actually used in the first example of the video, and we found that v dot w was negative 24. Now, the length of v would be the square root of v dot v, which is the square root of 2 squared plus negative 5 squared. That's square root of 29. And the length of w is square root of w dot w, which is square root of 3 squared plus 6 squared, which is square root of 45. Using the equation v dot w is equal to the length of v times the length of w times cosine of theta, we have that v dot w, that's negative 24, is equal to the length of v, that's square root of 29, times the length of w, that's square root of 45, times cosine of theta. So if I want to solve for theta, I have cosine of theta equals negative 24 over square root of 29 times square root of 45. So theta would be the arc cosine of negative 24 divided by square root of 29 square root of 45. And if you plug that into your calculator, you get something like 2.3 radians. So that's the angle between the vector v and the vector w. Let's do another one. Let v be the vector 2, negative 1, 1, and w be the vector 1, negative 3, negative 5. Again, these two vectors were used in the previous example, and we found that v dot w is 0. If I calculate the length of v, that's going to be the square root of 2 squared plus negative 1 squared plus 1 squared, which is square root of 6. The length of w is square root of 1 squared plus 3 squared plus 5 squared. That's square root of 35. So now using the equation, v dot w is equal to the length of v times the length of w times cosine of theta, we have 0 is equal to square root of 6 times square root of 35 times cosine of theta. Solving for theta, we have cosine of theta is equal to 0 divided by square root of 6 times square root of 35, which means that cosine of theta is equal to 0. Now, if I take the arc cosine of both sides, I get theta is equal to pi over 2 radians, or 90 degrees. So we see here in this example that v and w are perpendicular because the angle between them is 90 degrees. Now this happened because cosine of theta is equal to 0. And we got this equation because v dot w is equal to 0. We can say something about this in general. We say that two vectors are perpendicular or orthogonal if and only if their dot product is 0. So again, orthogonal and perpendicular mean the same thing. It just means that the angle between the two vectors is 90 degrees. Using this theorem, we can quickly determine if vectors are orthogonal. In this example, we want to determine if the following pairs of vectors are orthogonal. First, we have the vector u with entries 1, 3, negative 5, and v with entries 2, 3, 10. So again, to determine if they're orthogonal, I want to take their dot product and see if that dot product is equal to 0. So u dot v is the product of the first entries, that's 1 times 2, plus the product of the second entries, 3 times 3, plus the product of the last entries, negative 5 times 10. This gives me 2 plus 9 minus 50, or negative 39, which is not 0. So we can conclude that u and v are not orthogonal. Let's try another pair. Let x be the vector 4, 2, negative 1, and y be the vector 2, 3, 14. If we take their dot product, x dot y, we have 4 times 2 plus 2 times 3 plus negative 1 times 14. That's 8 plus 6 minus 14, which is equal to 0. So we can conclude that x and y are orthogonal. So that's it for this video. In our next video, we'll talk about dot products and projections.